In this video, we're going to talk about some important things to remember for the Geometry Regents exam. So the first topic that we're going to talk about in this video is parallel lines cut by a transversal. Remember that when we have alternate interior angles, we only know that they're congruent when we do have parallel lines cut by a transversal. So we would need to know that the lines are parallel first before we can say that the alternate interior angles are congruent. Remember, if you highlight your parallel lines and your transversal, you will see either a Z or a backwards letter Z if you have alternate interior angles. They're inside the lines and on different sides of the transversal. This is something to look out for in numerical questions that involve angles and also in proofs, a lot of times in triangle and quadrilateral proofs. We also have corresponding angles. Once again, corresponding angles are only congruent when we have parallel lines cut by a transversal, and corresponding angles are angles that are in the same position when the parallel line meets the transversal. For example, angle 1 and angle 2 here are corresponding angles because if you look where the parallel line meets the transversal, angle 1 is to the top and to the right, and so is angle 2. To the bottom right would be another set of corresponding angles. To the top left would be another set, and to the bottom left would be the last set. Corresponding angles are on the same side of the transversal, but one is on top of the parallel lines and one is in between them. When we have parallel lines cut by a transversal, if you know just one of the angle measurements, you can figure out the rest of the angle measurements using our angle relationships. For example, if angle 1 is, let's say, 100 degrees, then angle 4 also has to be 100 degrees due to vertical angles. Angle 1 and angle 5 are corresponding angles, top left, top left. So angle 5 also has to be 100 degrees. Angle 1 and angle 8 are alternate exterior angles. They're both outside the parallel lines, they're not within them. They're outside the parallel lines and they're on different sides of the transversal. So they also have to be congruent to each other. Remember, any two angles that are right next to each other when you have parallel lines cut by a transversal are supplementary because they form a straight line together. So if this is 100, then this one has to be 80 degrees. Once again, using alternate exterior angles, so does angle 2 have to be 80 degrees. And using corresponding angles, if angle 2 is 80 degrees, so is angle 6. And then finally, using alternate interior angles, if angle 6 is 80 degrees, angle 3, which is alternate interior with angle 6, would also have to be 80 degrees. So if you have parallel lines by a transversal, knowing just one angle measurement will get you all the other ones. Remember, all of the angle relationships that are true when parallel lines are cut by a transversal will also help to prove lines parallel. So if you're writing a proof that says prove two lines parallel, or if you have a question about making lines parallel, the way that you can prove lines parallel that come up the most often are number one, show that you have a pair of congruent alternate interior angles. If you can show that you have a pair of congruent alternate interior angles, that will prove that the lines are parallel. Number two, show that you have congruent corresponding angles. These are the ways that come up the most often. So depending on your question, whether you have alternate interior angles or whether you have corresponding angles, if you can show that they're congruent, that will prove that the lines that you want to be parallel are in fact parallel to each other. And fun fact about parallel lines, remember that they have the same slopes. Perpendicular lines have negative reciprocal slopes. Parallel lines have equal slopes. Another thing that people often don't remember is the right triangle altitude theorem. So remember the right triangle altitude theorem is occurs whenever we have a big right triangle with an altitude drawn to the hypotenuse, creating two smaller right triangles. Whenever I see this picture, this situation, I just think right triangle altitude theorem. So remember the first part of the right triangle altitude theorem says that all three triangles are similar to each other by AA. The big triangle, and the smaller right triangles are all similar to each other. And from those similar triangles come the altitude rule and the leg rule. So the altitude rule is used whenever you are given information about the altitude or when you have to find the altitude. And what the altitude rule says is that the altitude is the mean proportional between both parts of the hypotenuse. All that that means is that in the proportion, the altitude gets written twice so that it gets cross multiplied by itself. And in the other two spots go the part of the hypotenuse. The leg rule says that the leg is the mean proportional between the whole hypotenuse of the big right triangle and the leg's projection on the hypotenuse. That just means the part of the leg directly below the hypotenuse. So, for example, if you were going to be finding the red leg of the big right triangle, or if you were given information about the red leg, if this was the leg that you were interested in, that you had some information about, or that you were using, your proportion would put the leg in two spots so that it gets multiplied by itself. In the other spot, you'd have the whole hypotenuse of the big right triangle. And then the last spot, you would have the part of the leg that's directly, the part of the hypotenuse that's directly below that leg. In this situation, it would be AD. If you were focusing on the other leg, all would be the same, except you would be using this leg in these two spots. And for the projection, you would be using DB, because that's the part of the hypotenuse directly below this leg. Over here, we have a practice question. So if you pause the video and read the question, you will see that we are dealing with a big right triangle with an altitude drawn to its hypotenuse, creating two smaller right triangles inside. Whenever I see this picture, this situation, I think right triangle altitude theorem. I think either similar triangles, leg rule, or altitude rule. It does say that DC is 6 meters longer than AD. So if I represent AD as X, and I represent DC as x plus 6, that says that DC is 6 meters longer than AD. And what the question is asking for is the length of the whole segment AC, the whole hypotenuse of the big right triangle. Since I have information about the altitude, and this is a right triangle altitude theorem question, I'm going to jump to my altitude rule. So when I set up my proportion, the altitude is going to be written twice so that it gets cross multiplied by itself. In one of the other spots, I'm going to put one piece of the hypotenuse, and in the other spot, I'm going to put the other piece of the hypotenuse. Now, all I have to do is cross multiply. Remember to distribute the x in both spots. And this question worked out to be a quadratic, so I do have to factor here. So in order to factor, I'm going to make my equation equal to 0 by subtracting 16 from both sides. And I'm looking for two factors of negative 16 that add up to positive 6. And I'm thinking 8 and 2. And 8 would need to be the positive one. 2 would need to be the negative one. 8 times negative 2 is negative 16. And 8 plus negative 2 is still positive 6. So our two solutions here are x equals negative 8 and x equals 2. It doesn't make sense for our x value, which is a segment of a triangle, to be negative, because otherwise we wouldn't be able to see it in the picture. Negative. And often in geometry, since we're talking about real world objects, we often reject the negative. But be careful here. The question wasn't asking for the x value. It was asking for the length of the whole base AC. So that would be the 2 part. 2 plus 6 is 8. So the whole segment AC would be 10. So that is my final answer. Moving along, I have one more example just so we can see how both of the rules work. So here, once again, just from the picture, big right triangle with two smaller right triangles inside. So this is right triangle altitude theorem. We're finding the length of arc Q. And this time, I don't have any information about the altitude. We're not finding the altitude. We don't have it, so we're not going to be using the altitude rule. What we have here is information about one of the legs. So I'm going to go to leg rule. And what the leg rule says is that the leg is the mean proportional. So it gets written twice so that it gets multiplied by itself between the whole hypotenuse, which in this case is 17. That's the whole hypotenuse of the big right triangle. So that goes in one of the spots. And the part of the hypotenuse directly below that leg. So the part of the hypotenuse directly below this leg would be QR, which is what we're finding. We don't know what RQ is. So from here, I'm just going to cross multiply. 17x equals to 15 times 15, which is 225. And now I'm going to divide by 17. And the question does say the round to the nearest tenth. So that is approximately 13.2 units. So the length of RQ is approximately 13.2 units. And I think it is worth mentioning that you can actually do this question without using the leg rule from using similar triangles. It just is a little bit more work because if you notice, we have information about the big right triangle. We have two of its sides. We have 17 and we have 15. And we have information about this smaller right triangle over here. We are looking for one of its sides, and we have the side that's 15. The problem is that the triangles are just facing different directions. So you would have to orient them the same way. So I'm just going to read the big triangle so I can show you what I mean. So this is the big right triangle. So I'm going to highlight that in red right now. That's the big right triangle. So I'm going to put the right angle here. So that would be P. And I'm just going to imagine that I'm rotating the triangle upwards so that R is on the top and T is over here. And now I'm just going to redraw the smaller right triangle over here, the one that we're trying to find the side of, so that it's facing the same way. I want to put the right angle in the same spot, so that would be Q on the smaller triangle. The big red triangle and the smaller green triangle share angle R. So angle R has to correspond to itself. So if angle R is over here in the big triangle, angle R has to be here in the small triangle. And that leaves this point to be P. So now if I relabel the triangle, PR is 15. We have QR is 17. Oh, sorry, TR is 17. And we are looking for QR. Now, if we set up a proportion with corresponding sides from the similar triangles, I'm just going to do small over big equals to small over big. And notice that we have basically the same exact proportion. It will cross multiply the same way. So in a lot of instances, the leg rule and altitude rule do make life easier. If you know them, you can do things very automatically. But in a lot of instances, since we are working with similar triangles here, you can just redraw the triangles so that they're facing the same direction and set up and solve a proportion. There's only some situations where you wouldn't be able to do that, but in most situations, that method would work as well. The next thing that we're going to talk about is partitioning a line segment into a given ratio. So there is a formula for this. For example, if we wanted to partition this line segment in a 2-to-1 ratio, but I am not going to use the formula. I'm going to use a set of 3 steps that does the exact same thing as the formula. So I'm going to do the same 3 steps to find the x coordinate and the y coordinate because my point that I'm finding should end up being an ordered pair. So the change in y. The change in x is x2 minus x1. And this is a directed line segment. So we do have a start point and an end point. So our x2 is going to be 10 and our x1 is negative 8. So that is 10 minus negative 8. I'm also going to find the change in y. So this is our y2 and this is our y1. So that would be negative 2 minus 4. So let me put down what each of these is. 10 minus negative 8 is 18. Negative 2 minus 4 is negative 6. Now our multiply by fraction. Now we're given the ratio as a ratio, a 2-to-1 ratio. But if there's a 2-part and a 1-part to the ratio, that means we're splitting up the line segment into 3 parts in total. So the fraction that we're going to be using is the total number of parts as the denominator. So in this case, that would be 3 as the denominator, and the number to the left as the numerator. So the number to the left of the ratio here would be 2. So the fraction that we're going to be using is 2 over 3. The number to the left over the total number of parts in the ratio. So I'm going to take our 18 that we got from step 1 and just multiply by the fraction that we just created. I'm going to take my -6 from step 1 and just multiply it by the fraction that we created. So 18 times 2 over 3 would be 12, and -6 times 2 over 3 would be -4. And there's one more step. We're going to add the start coordinate. So for example, for the x coordinate to our result, 12, we're going to add the starting x coordinate. So the x coordinate from our start point was -8, and that gives us 4. And to our y value that we found before, we're going to add the starting y coordinate. So the y coordinate from our start point was 4, and that's 0. So that's our x coordinate of the point that we're looking for, and that's our y coordinate. So the point that divides this line segment in a 2-to-1 ratio is the point 4, 0. If you have a different way to do it, if you do have the formula memorized and you like to use it, you can feel free to do that. But this way works in every situation when you're partitioning a line segment into a given ratio. The next thing I want to talk about is trig, very, very briefly. So when we're doing trig, remember that first of all, your calculator has to be in degree mode. When your calculator is reset, you do have to go to mode and change it back to degree mode. The second thing is make sure that you are using trig only for right triangles. Trig does not work unless your triangle is a right triangle. So if you pause the video and read the question, you'll see that what we're looking for is angle theta in this diagram. So a lot of people try to use trig. They try the label in this triangle over here. From that angle, they try the label opposite, adjacent, hypotenuse, and set up a trig ratio. But the problem with that is that this triangle here is not a right triangle, so that is not going to work. So in this diagram over here, we do have two right triangles. We have the large right triangle, and then we have the smaller right triangle. So our plan here would be to use the right triangles to get information about the non-right triangle. So from the big right triangle, we could find this whole angle. And from the small right triangle, we could find this angle. And once we have this angle and this angle, we can subtract to be left over with the angle that we want. So you could pause the video and try this out, but we would need two trig ratios over here, one for the right triangle and one for the small right triangle, and then we can subtract them. Also remember that even though the question says to round to the nearest tenth, do not round until your very last step. Otherwise, you might round early and get a rounding error that might deduct you a point on the Regents exam. Until your very last step of the question, always leave 3 to 4 decimal places so you don't round early. The next thing I want to talk about is transformations. So here I just have the rigid motions, and rigid motions mean formations that produce congruent figures don't change the side lengths, and that would be transitions, rotations, and reflections. So reflections are just mirror images. So if you graph your figure and you know what line you're reflecting over, it's super easy to do a reflection. You just count the spaces to the line of reflection from the point and then just move it in equal number of spaces onto the other side of the line. Rotations can be a bit trickier, especially if you are having trouble visualizing where the rotation is going to land the figure. So I do recommend having the rotation rules memorized. Look at them right before you exam in your mind. That way, you have the rotation rules to use, and you can guarantee that you get every rotation question correct, especially if you've been using them in class. If you've been relying on them in class, you need to have them memorized, otherwise, you are not going to have them on the Regents exam. For reflections, for any straight horizontal or vertical line, like the x-axis, the y-axis, or any other horizontal or vertical line, like y equals 2, x equals 2, any of that stuff, super easy to do graphically. When we're talking about slanted lines, like y equals x and y equals -x, that might get confusing counting diagonal boxes. So you might also just want to remember these two rules for reflections. That way you have that down for the Regents exam. Remember, there are only 3 rules for rotations, and I just made a picture over here illustrating why. So over here, notice that if you rotate 270 degrees clockwise, that's the same thing as 90 degrees counterclockwise. So that's why they both have the same rule. The 270 degrees clockwise rule is also the 90 degrees counterclockwise rule. 180 degrees in both directions will land your point in the same spot. So that's why 180 degrees has the same rule no matter what the direction is that you're rotating in. And over here, 90 degrees clockwise and 270 degrees counterclockwise will land your point in the same spot. So they are the same rotation. So that's why they also have the same rule. Remember, when the question doesn't specify, it is always assumed that we are rotating in a counterclockwise direction, centered at the origin, unless the question otherwise states. Here, I have a list of the quadrilateral properties, and that is something that you definitely need to know for the Regents exam. So if you do not have them memorized, you need to know them, and that is something that you definitely need to study. Remember, there are 5 properties of parallelograms, and you can read them here. And there's also 5 ways to prove that you have a parallelogram. The one way that's not listed here that you can use to prove a parallelogram that is pretty important is that in your quadrilateral, if you have one pair of opposite sides that is both congruent and parallel, that will prove it's a parallelogram. Feel free to pause the video so you can grab a picture of this list or write them down. Here we have our rectangle properties. There are just 2 that make them different from regular parallelograms. If you need to prove that you have a rectangle, you have to prove it using one of these 2 methods. If you're proving that you have a rhombus, rhombuses have 3 special properties that make them different from regular parallelograms. You would need to prove that you have a rhombus using one of these 3 properties. And finally, a square is a rhombus and a rectangle. We also do have one other quadrilateral, a trapezoid. You do need to know what a trapezoid is and what an isosceles trapezoid is. So that is definitely something to review as well. The very last thing that I do want to talk about in this video, because this video is getting a bit long, is I want to talk about this proof over here because it uses something that might come up on the Regents exam. So over here, I see that we have a quadrilateral, and in fact, question, if you pause the video and you read the question, it says that this is a square. So remember, we know a lot of stuff about squares. It has all the properties of rectangles, rhombuses, and regular parallelograms, which it has to be first. It also says that BE is congruent to FC, and we are proving that AF is congruent to DE. So notice that AF is the side of this triangle over here, and DE is the side of this triangle over here. So a lot of times in quadrilateral proofs, it comes down to proving triangles congruent or similar. Since I want to prove AF congruent to DE, I don't want to prove a proportion or a product. I want to prove sides of the triangles congruent. That tells me this is going to be CBCTC. Corresponding parts of congruent triangles are congruent. So before I can use that, I first need to prove the triangles congruent to each other. Now, if I think about what I know about squares, I do know that the opposite sides are congruent to each other, and I do know that squares have 90-degree angles. Now, I have information about BE and CF, but I would need the full side BF of the blue triangle and the full side CE of the green triangle. Luckily, both of those sides overlap at EF. That's what's shared by the reflexive property. So remember, if you're starting with 2 congruent segments and you're adding on a congruent segment to both, you can use the addition postulate in order to do that. So we can say this plus this is congruent to this plus this, and therefore BF is congruent to CE. I'm going to just write up this addition postulate part so that way you can see that. So if I was writing this up in a proof for just the addition postulate part, one of my steps would be BE plus EF is congruent to CF plus EF. And my reason for that would be, oops, I'm writing subtraction, but that's addition clearly, would be addition postulate. And then after that, I would say BE plus EF is BF, and CF plus EF is CE. And that's by substitution because we're saying that we're replacing something, we're replacing the addition with what it actually is, with something that means the same thing. If you were writing up the rest of the proof, you would need to put that you have the congruent right angles. You know that you have congruent right angles because all angles of a square are congruent right angles. And you would need to put that these opposite sides are congruent. And the reason I know that is opposite sides of a square are congruent. And I almost forgot. Before you can use your addition postulate, very important, before, because you have to start with congruent and be adding uncongruent, you do need to say that EF is congruent to itself because that's what you're adding on to both, and that would be by the reflexive postulate. So that would need to come before the addition. And then we would have the triangles congruent by SAS. And from there, it's one more step to CPCC to prove the two segments that we're interested in congruent.